Hi, let us talk about generic types, traits, and lifetimes. To handle duplication of concepts, every programming language has some tools. In Rust, it's called generics. Generics allows us to build code that can be used with various data types without having to rewrite it for every data type, which makes lives easier and reduces the likelihood of programming errors. So in this video, we'll talk about how to define our own types, functions, and methods with generics. We'll also talk about how to minimize code duplication. Let us first go through how to extract a function. Then, using the same method, we will combine two functions that only differ in the types of their parameters to create a generic function. Also, we'll go through how generic types can be used in structs and enum definitions. Let us take the example of a program which tries to find the largest element in an array. So here we have an array which is called number list, and we have a mutable variable called largest, and that is pointing to the first element in the number list. And here we have a small piece of code which runs in the for loop, which is going to compare the largest with the number, which is going to basically compare two different elements, one after the other, one with the other, to see which of them is the largest. Whichever is the largest is updated to the largest variable. Then we print the same using the println statement. So let us take another example where we have to perform the same task but for two different arrays. Here we have an array with certain elements. Here we have a different array with with a different set of elements. So the basic functionality remains the same. We're trying to find the largest number in both the arrays, but we have to rewrite this snippet of code all over again. So that is one case. One way to minimize that, one way to reduce that repetition coding is we see that the basic functionality remains the same. That is, in both the arrays, we're trying to find the largest element, largest number. So we can basically put it in a function and call that function as and when required. So here we take the largest function, which has a parameter called list. This represents any concrete slice of i32 values that we might pass into the function. As a result, when we call the function, the code runs on the specific values that we pass in. So we take this largest function and we pass this list, which is of i32 type. In the list we can see we can pass this first array that we have and return the value, and have the second array pass and return the value. We can basically call the largest function as many times as we want, as long as the type remains the same and the return type is also same. So in summary, we can identify the duplicate code and we can extract the duplicate code into the body of the function, and then we can specify the input type and the return value type of that code in the function signature. So we can update the two instances of duplicated code to call the function instead. So let us see what is generic data type. We use generics to create definitions for items like function signatures or structs, which we can then use with many different concrete data types. So in the previous example, we could see that we had to particularly pass i32 type, but by using generics, we don't have to particularly pass a single type. Instead of a particular type like i32 or string, we could just use a generic called t or any other variable, and that what type is getting passed could be determined at the compile time. That is what generic basically does. So we can use this to create definitions for item functions, signatures, or structs. So basically, when we define a function that uses generics, we place the generics in the signature of the function, where we would usually place the specific data types of the parameters and the return value. We read this as the function largest is generic over some type t and this function has one parameter named list, which is a slice of values of type t, and the largest function will return a reference to the same type t. Basically, instead of mentioning what particular input and output this largest function takes, that is which data type, instead of that we can put a box here and call that as a generic. Here we have one function called largest i32, which basically takes the input type i32 and returns an i32 value, and the function is trying to find the largest item in the list. And here we have the largest char function, which takes char type of data as input and returns char type of data, and it is also going to try and find the largest element in the list. So in the main function, when we have i32 type of data, we call the largest i32 function, and when we have character type of data, we call largest char function. So these are two functions that differ only in their names and the types in their signature. So the largest function using generic type parameters. So how can we improve that function? So if I take a largest function, and if that function is generic over type t, which means I'm not specifying whether it is i32 type that I'm passing or char type that I'm passing, but I need to pass whichever input type I am giving, I should expect the same output type as well. So here I'm taking a generic type t. In the main function, I could use this same snippet of code to run on the i32 type as well as on the char type. That is the point of using a generic. But as you can see, this code does not compile yet. If we try to compile the code, it gives us an error saying that the standard comparison partial order, which is a trait, and we'll talk about that in the next section. For now, we can know that this error states that the body of the largest won't work for all possible types that t could be, because we want to compare values of type t in the body. We can only use types whose values can be ordered. To enable the comparisons, the standard library has the standard compare partial order trait that we can implement on the types. So this basically tells us that if we try to restrict the types valid for t to only those that implement the partial order, then this example will run. We'll fix this in a later video. So we can implement generics on structs as well. So let us see how to do that. So the syntax remains the same, that the parameter that is generic has to be written in between angular brackets right after the definition. In the previous case, definition of the function, in this case, definition of the struct. So the struct is called point. Right after point, we implement the generic. That is, we say that this struct point is generic over t, and the values x and y will also have the type t. Now this particular type could be i32 or could be a floating point as well, f64. So here we see that we're taking an integer, we're taking a variable called integer, and the type that x and y are going to have is integer type, i32 type. But here in the floating point, we're taking f64 type. Both of this is supported because the point is generic over t. But here we can see that if I take x as t and y as t as well, but if I try to run this piece of code, here the x is taking an i32 type, but y is taking f64 type. That is not allowed because we have mentioned here that the point is generic over one type. At compile time, x and y, both of them should be assigned same data type. So we're going to get an error saying that this is mismatched types. if we want to fix this, we can simply change that point will take two different generic parameters, that is t comma say another variable like u, t comma u. That in that case x would take t and y would take u. So x could be an integer and y could be a floating point. Now let us see how to implement the generic type in enums. So even in enum we can implement the generic type and the syntax pretty much remains the same. Right after the name of the enum, that is option, we have to implement the generic type between the angular parentheses. So option can take two different variants, that is sum and none. Sum is going to return a value of some data type, that would be t, and none is not going to return any value. And in another case, enum result would return two different types of values, that is OK, that is if the result is successful, if the operation is successful, then the result would return OK, which would be of type t. If there is a failure, it would return error, which would be of type E. Next, let us see how generics work with methods. Here we have defined a method called x on point t that returns a reference to the data in the field of x. So what we're trying to do here is trying to implement the generic type in the method. So because we're doing that on this method, we have to implement the generic type t right after the implementation block, so that we can use this t to specify that we're implementing methods on the type point, which is also generic over t. So we could use two different generic parameter here, say t and u or u and v, but since both of them are returning the same type, we have used the same t parameter here. Now let us see how an implementation block can apply to a struct with a particular concrete type of generic parameter type t. So here we have struct point with generic parameter t, which means that both of its variables x and y are going to be of that particular data type, and here the implementation block says that the point is going to be generic over f32 only. This point t has a generic type of t, but also it could have a very particular case as in f32, which is described by this point. Let us see another case where this example basically shows that the generic type parameters in a struct definition need not be the same as the one that we use as well. Here we see that f32 is a particular case of this point t, but this f32 is applicable only to this block of code. And here we can see that in the implementation block, even though it says that the generic parameter is x1 and y1, in the mixup function what is implemented is x2 and y2. This basically shows that generic type parameters in a struct definition, that is this, need not be the same as the one that we use in the method signature, that is this. So here what is happening in the main function is we take point 1 and point 2 and we use this mixup function to create a new point called as point 3. So here when we try to print, the p3 dot x part takes, which is the first x1 part, that is here we have declared that as 5, and the dot mixup of p2 part will take this part, that is y of c, that is the y2 part, and we print y2 part here. So this shows that the mixup function could have a different type of generic than the one that we have used in the definition of the struct. So one thing about this generic type is that instead of specifically telling which data type is being used, whether it is i32 or string or f64, we can use a type called as t, which is generic to a function or a method or a struct or an enum, and at compile time it could be anything. At compile time we would get to know which particular type is there. Rust assigns the data type at the compile time. So if we were wondering if assigning generic types would make the program run any slower, then that is not the case. This statement stands true because of something called as monomorphization. This is a process of turning generic code into specific code by filling in the concrete types that are used when compiled. So basically Rust compiler at compile time does the exact opposite of what we have done. Instead of specifically saying whether the function is taking an i32 or a different type of data type, the concrete data type, we mention a generic data type. So in the process of monomorphization, the generic data type is translated into the specific code. Here we have taken an example. In the main function, we take integer of sum and floating point of sum 5.0. So this is what the compiler would roughly translate that as. When we write it in the generic type, this is what it would translate it as. So option i32, so some variant would have the i32 type, and in case of option f64, some variant would have type f64. The generic option T would be replaced with specific definitions created by the compiler. Because Rust compiles generic code into code that specifies the type in each instance, we pay no runtime cost for using generics. So when the code is actually running, it would just perform as if we had duplicated each definition by hand. So the process of monomorphization takes care of this and makes Rust's generic extremely efficient at runtime. Thank you.